guys had
Okay. That's new.
yeah. I hope you guys had a good weekend. Appreciate all your hard work you did last week. I think we're progressing very well. Today, Mr. Jordan Clark is going to take care of our safety meeting, so I will go ahead and turn it over to him. And Jordan, take the show, baby.
I just have a little one minute clip I found just about work safety. Am I supposed to share it to the screen? How does this work?
Yep.
Share the screen.
Okay.
Faster.
Let's see. I'm guessing you put share. Is it desktop?
You can do it that way, or you can share the individual window by itself, like the browser. Should show up in there too. Either way.
Okay, let's just do this one. Let me know what you guys got so far.
We have a trees and a nice little white house and
A blue truck.
a blue truck.
So y'all got the little video up?
And we got the little video up. Now we got a big video up. Go ahead.
All right, play it.
Yes, sir.
All right.
Tell you what, I'll make you a deal. You have that room cleaned today by the time I get off work, and we'll work on that doghouse.
Deal.
I love you, buddy.
Okay.
People don't think that accidents can happen to them, but they do out here. Whoa. Hold on, hero. Let me help you. Dear Gene, I found your drill. Sorry I couldn't get it to you because I was texting, wasn't paying attention where I was going, and I fell down a hole and died. Be safe. You gotta look out for the other guys on your crew. It's not easy being green, eh, rookie? Earl's gonna ride you, but you follow his lead. You do something stupid, you hurt somebody else, it's a million times worse.
Be safe.
Whoa, close up deck. I got guys up on 5 within railings.
We really waiting?
Not for long. They're living the real one. This is the fastest way to do it. What if it was faster to cut some corners? That is the cleanest room I have ever seen. One of those corners where they're cutting you. Most important responsibility is keeping your coworkers safe.
Where are you?
All right, that's it.
So really, I mean, it just looked like a commercial about other video, but it did go through a lot of clip situations there of things that you saw that was going wrong. And I would suggest if anybody chimes in there, what did you see in the video that you saw was wrong? Did anybody watch the video?
People were texting.
What was that, Lucas?
I said that people were texting at work.
Texting at work, that's a good one. And why don't we hold there for just a second? Are phones allowed while you're working on in the utility?
No.
No, you might as well leave them in a truck. For one thing, no texting and driving at the same time. That's a CDL thing. And phones have to be in your fleet when you're working with electricity.
Okay.
Okay. What else?
I saw the buddy system when they're lifting something heavy.
Right. That was good. It looks like they're bending their knees, right? Which is a good thing to do. What else?
A lot of them had on markers.
These are not the droids you were looking for. That was kind of R2-D2 on us. What else? Trip hazards. I saw some trip hazards in there. I think the guy tripped over a can. There was one point in there where they were working out around a spot and there was no fall protection. And then no barricades for fall protection. Then they were doing some lifting at one point that was open down to the next floor down. Don't stand under suspended loads. A lot of things going on in those short little clips right there that you need to look out for.
Right.
Jordan, anything else you'd like to add?
No, not really.
All right, so guys, I mean, I think that was the first student safety meeting,
Yep.
right? Okay, that's typically how they run.
Yep.
So who's going to be next? Jordan jumped up on that one, took care of that. Mr. Bythway.
By the way,
Yes, sir.
Okay, you will be, everything works out to plan. You will be Wednesday when we have our Zoom class.
Yes, sir. Sounds good.
All right, sounds good. Okay. So, Professor V,
Yep.
where did we leave off?
17.
17. Unit 17, we were starting in percentage.
We finished it.
We finished percentage.
Yeah, we got to 17.
We're going to go into a little bit more of percentage this
Yeah.
morning. So stand by. Swap some screens around here. Ooh, somebody's breaking out the chips, it sounds like. By the way.
Yeah, I got some chips.
Okay.
Got a little hungry this morning.
So let's see. Bang. Let's go back to images. I've got the super slow computer this morning again, Professor Bill.
Super slow.
Mm-hmm. Okay, while we're talking here, what's the purpose of a transformer? What does a transformer do?
It transforms high voltage into lower voltage to be able to go into homes.
Okay, very, very good explanation. Do you think there is transformation at higher voltages? Say you have a transmission voltage, really high voltage. Do you think it transforms down to another voltage before it gets to your home?
Yes.
Okay, good. Those are great explanations right there.
Because going into your house is what, 120, 240 or something like that.
Mm-hmm.
And coming from a substation or a generation station would be hundreds of thousands of volts. Or
Who's doing the talking there? Because that sounds like
Ryan.
that sounds like
Ryan
Edward to me. Yeah. All right. I'm going to bring up a picture of a nameplate that of a transformer. All transformers have nameplates and information plates on them, from the largest to the very smallest. And it's got some information on it we're going to learn about, and you guys are going to have to do some math in the process. So share screen, share that one, share. Okay, y'all see that?
Not yet. Yep.
Okay, perfect. Now we'll get really in depth with transformers and their use for one, and the math that goes along with it. You'll notice on this transformer, up on the upper left-hand side, it's got what they call a kVA. The kVA acronym stands for kilovolt amperes. Let's work with the K. What does kilo mean? Ones, tens, 1,000s, 1 millions, tens of thousand. So 1,000 VA, 1,000 volt amperes, and it's got a numerical value of what? What's the number right beside it?
15.
15. So it's a 15 kVA transformer. All right, guys, loosely translated, and this is very good for the lineman side of it. An engineer is probably going to tell you a little bit different because of heating of the transformer and capacitance and a whole bunch of other factors that are going here. But a decent rule of thumb for us is 15 kVA translates into 15,000, because we have K, watts. 15 kVA translates to 15,000 watts. Now, what if that number was 25? How many watts would this transformer produce?
25,000.
25,000. There you go. You got 3s, 5s, 10s, 15s, 25s, 37s and a half. I mean, it goes, there's a whole range of different size transformers out there. We'll work with this one for a little bit. 15 kVA translates into 15,000 watts. Now that's in the lineman world. If you go up to an engineer and you say, well, I've got a 15 kVA transformer, that's 15,000 watts. He might put some mumbo jumbo on you. Well, you're not accounting for this and you're not accounting for that. But as a good rule of thumb for a lineman out there in the world, 15 kVA translates to 15,000 watts. Let's talk about the watts part just a little bit. Watts is the power, correct, that we're able to produce. So a good way of thinking this right here, I've got a baseball field. And around that baseball field, I've got 15 1,000 watt lights. Turn them on at night. Will this transformer be able to power those 15 lights?
Yes.
Yeah, because 15, each individual light's 1,000. So this transformer will be able to power 15,000 watts. That's just a simple rule of thumb. Now, when
Quick question.
Yep.
If you had 16 of those lights, would all the lights still power, or would they just be at a dimmer?
They would, and there's a lot of variables and factors that are going on here. There is actually a lot. There's 150%, which we're going to get into deeper. There's a transformer will go to 150% for a short-term period. Over by, 1,000 watts. Yeah, that's not going to be a problem. There are some variables in there that's going to work, and we'll talk more in depth about that later. But no, they're all burn fine. Now, if you've got, let's say we put 30 lights out there, 1,000 watts, and we've got a 15 kVA transformer, pretty much the transformer is going to overheat and die, or a fuse is going to blow on the transformer, melt out. Fuse is going to melt out in the transformer. It just won't be able to power those lights.
Gotcha.
Okay. So for this purpose, we're just going to use this 15 kVA. Now you'll notice just to the right of that, it's a percent sign, IMP 85 degrees Celsius. So this transformer, when it's 85 degrees Celsius, has an impedance, and we'll talk about impedance just here in a moment, of 2.6%. Anybody got any idea what impedance is? If Professor V was out there at the field and he's come running at me because he didn't like something I said to him, and I put my arm out and tried to hold him back, would that be me impeding him from knocking me out?
Yes.
Yeah, I'm impeding him. I got my arm out. I'm slowing him down, trying to not get clocked because he hits hard. All right. So I'm trying to slow him down. That's what impedance is. I'm impeding something from going from one place to the other. It is very similar to, and I don't mind if you guys say this, just know the difference between the two, resistance. All right. Just know the difference when we get this explanation right here. Resistance on its own is I have a component or a piece of electronics that has a resistor in it. Okay, an electronic resistor. That's an electric component. Impedance, on the other hand, in a transformer, I don't have any resistors in there, but there is a certain amount of percentage of impedance. It's slowing the flow of electricity now. Where do you think that impedance comes from?
It could probably be a number of different things, I would imagine.
Give me some.
Temperature, moisture.
Okay, temperature will determine a factor in there. We don't get into that much. Moisture is not. Transformers are fully self-contained and immersed in oil.
Did not know that.
Anything else?
How far the transformer
The transform age. Anything to do
The
with it?
wire, I mean, yeah.
We talked about it a little bit last week. Is there a perfect conductor? Never.
No.
No, there's not. Okay. All conductor has some form of resistance in it. All right. Transformers are made of multiple windings around cores. Windings of copper around cores. So do you think that the impedance is coming from those windings? There's no perfect conductor going through there. I don't even mean miles of windings in some transformers. Is that a possibility?
Yeah.
Okay, that's what it is. All right. All of that conductor that's wound and wound and wound around the cores of a transformer are not perfect conductors. So they impede electricity by a little bit, not very much, only 2.6%. So here we are, we're going to get into some math. This is a 15 kVA transformer. It would produce 15,000 watts, but it is impeded by 2.6%. What is the true kVA? So what's 2.6% of 15? Let's see if we can talk through this math a little bit. Now, my normal practice is to convert the percentage into a regular decimal number. How do we do that?
Divided by 100.
No. How do we convert a percentage number, 2.6, to decimal?
Divided by 100.
Move the decimal point.
Move the decimal point. How many spaces?
1 to the left.
Correct. All right, so I've got 2.6. I'm going to move the decimal place 1 to the left, and I have 0.26. I've now converted my percentage to decimal.
So would it come out to be 11.1 kilovolts?
I'm not there yet. Okay. After we have converted, hold that answer because I don't know yet. I haven't put in my calculator. So we've converted to 0.26. What do we need to do to 15,000?
Would that not be 26? Would that not be 26%?
0.26. Who said 26? Okay, you got to move your decimal place to the left. Okay, gentlemen, take your 15,000 and multiply it by 0.26 on your calculators. What do you get?
I got
3,900.
3,900. Okay, subtract that from 15,000.
Wait, what?
Subtract that from 15,000. What do you have?
11,100.
All right, and who gave that original answer? I think it was Embry.
I don't think that's right.
Yeah, I don't think that's right either. That's what I was saying. I think it's 15,000 times. You said 2.6, right? 2.26. 0.26.
0.26.
What was your original number, Professor?
I've got 15,000 multiplied by 0.26. What is that thrown into a calculator?
No, but your I'm not trying to be rude, but your decimal should be 0.026.
There you go. Thank you very much. 2 spaces to the left.
Twice.
Not one. 15,000 times 0.026 equals
I got 435.
435, thank you. 435 minus 15,000?
14,565.
565. Thank you very much. Okay. Now you got to watch out, especially when it comes to quizzes and tests. All right. I asked you for the true kVA of the transformer when you include an impedance. Is 14,565 kVA or watts?
KBA.
It'd be both, wouldn't it?
No. All right, hold on one second. If I have a 15 kVA, that's 15 kVA. If I have 15,000 watts, that's 15,000 watts. The number I have just calculated and come up with is 14,565 watts. What is that in kVA? Move your decimal point from the 5 at the end over 3 places. 1, 10, 100, 1,000. You should have 14.565. You have now converted to kVA. I am, but
Are you doing your Wacom? Oh, never mind. I thought you were calculating.
no.
Because we can't see it.
You can't see the.
Yeah, we got the,
Okay.
Yeah, we got the Howard instructions.
We'll go with this route. Okay. In fact, we'll draw it out to make it better. So let me unshare this one. Stop share. And let me share screen. We're going to do a whiteboard. Share. Okay. Y'all see this white? No, you don't.
Yeah.
Do you see the whiteboard?
I got a white screen.
I mean, it's white. It's. I mean, well, now I see Professor Verman.
Yeah, well, that's pretty bad.
Hey. It was a good weekend.
There we go.
Yeah.
So let me move all this stuff out of the way. And we will draw in what we're supposed to have. There we go. All right. Wacom time. It's time to Wacom.
Wake up.
All right, here we go. So we had a 15 kVA, correct?
See, senor.
Great, it's not working.
Uh-oh.
Here we go. A 15.
Yeah, I see it.
Your pen's not working. All right, so see if we can do this by mouse. A 15 kVA. This is not good. And we converted that to watts. 1, 5. Yeah, this is awful. 0, 0, 0. All right. What was 2.6% of 15,000? I had to change screens so I don't have that calculation anymore.
390.
2.6% of that is 435.
435. So we subtracted 435 from 15,000 and came up with what?
14,565.
All right, 14,565. Remember in the beginning here, we changed 15 kVA into watts. And once we did the calculation of the 2.6%, our answer is still in watts. 14,565. I need it converted back to kVA. So at the 14,565, At the ending 5, I need to move over 1,000. So move the decimal point 10, 100, 1,000. You should have 14.565. You've now converted it back to kVA. Your Wacom's not any fun at all, Professor V.
Whoops.
I could do better typing it out in Notepad. So I'm going to stop that share. All right, I know that kind of sound pretty funky. Is everybody, as far as a nameplate and an impedance concerned, and we'll do some more, know how to figure the percentage losses, and that's impedance. Remember, impedance is a loss, so that's why I subtracted it. That's why I took it away of a transformer. What time is it?
8:30.
We'll do one more here. Let me share another screen. I don't know what the deal with this is. Okay, so I'm going to share screen. Let's try screen 1. Share. Okay, you should see my old transformer picture up again.
Yep.
Okay. Get rid of that. Let's try another one. Yep, it's got the information on it. Boom. So, okay. So I'll see if I can do this in Notepad and do it on the side of the screen here. Hold on. Wow, this is warp factor. Here we go. All right, so let's do a little reading here. Can anybody give me the kVA of this transformer by reading the nameplate? I don't know how clear it is for you guys. Can you read that number right there?
750.
750. All right, convert that into watts. That's kVA, convert that into watts.
750,000 watts.
750, and then we're gonna do 1,000. 10, 100, 1,000. So 750,000 watts. Let's go ahead and get this off to the side here. So 750 kVA.
Mr. Shoemaker,
Yes, sir.
is it 750 watts or 750 kilowatts?
Kilowatts is 750 kVA. Or it's 750 kilowatts. Or it's 750,000 watts. All three of those things are the same.
So it's not 750, 862?
862. No. That's just information off to the side. Use
Okay.
the 750.
All right.
Good question. Okay. What's my impedance on the transformer?
5.6.
5.6. Okay. So what we're going to do here is we're going to take 5.6% and convert it to decimal. 0.056. That's the percent conversion to regular decimal. My next part is 750, that 1, 2, 3,000 times 0.056. Can somebody come up with that solution? Because I'm doing multiple things on my.
I got 708 kilowatts.
You can't. that we're not in kilowatts. We're in, so my number right here is 750,000.
I got 420,000.
420,000.
That's what I got.
Anybody else? Anything else?
Oh, wait a minute.
4,200.
42.
Well, that's
4,200.
4,200, 4,200, that's two.
Had 42,000.
42,000.
Yeah,
Watch the way you're
42,000.
punching this into a calculator. 750,000 times 0.056. We've got multiple answers going on out there.
That's what I did. I got 42,000.
42,000?
Yeah, that's what I got.
my bad. I gave you the final answer. I'm sorry. I didn't mean to confuse you.
No, that's no
I
problem.
got 400 and
What was that, Nigel?
420,000.
430,000.
Did you do
20,000.
0.056?
420,000. Stand by. 750. 1, 2, 3. That's 750,000 times 0.056 equals 42,000. That's the direction I threw it in the calculator.
Yes, sir. That's
Okay.
what I got.
Yeah.
All right.
Okay, I got 42,000.
Yeah, 42,000.
42,000. 1, 2. Yep. Okay. 42,000. I'm going to subtract 7. Excuse me for the keystroke right there. 5, 0, 1, 2, 3 minus 42,000. What does that equal?
708,000.
708, 1, 2, 3,000. All right. Now you got to watch what I'm going to say in the question as far as the test or quiz is concerned. If I ask you on the quiz, I need you to convert what is my wattage losses with this transformer nameplate. What are my wattage losses? Is my answer right now in watts?
Yeah.
Yes.
Hold on. Yeah. Yes, it is.
It's still in watts. I haven't converted it. If I ask you what is the true kVA, I need to move over. Now watch my cursor on the side here and get rid of the 10, 100, 1,000.
708 kVA.
There you go. 708 kVA is my true kVA.
I gotcha.
All right. So the person that's talking out there, is it 750 kVA? Is it 750 kilowatts? Is it 750,000 watts? All three of those are the same. But once you convert it down to watts one time, leave it that way until you get the solution. Because I might be asking for, just like you just said, I might be asking for an answer in kVA. I might be asking for an answer in watts. I might be asking for an answer in kilowatts. But save it until you get that 708 numeric value. Then convert it as needed. All right, it's 8:36. Let's take about 14 minutes and be back here at 8:50. I don't like that. When did they start doing that? Okay. Do I still have a share screen up? I don't.
Negative.
All right, stand by. Screen one. I get the feeling that everybody's not really warm and fuzzy on this yet, so we'll do another one. All right, you should have a transformer nameplate up and my little notepad on the side.
Yes.
Okay, sounds good. All right, so we'll pick on some people here. Lennon, because you're showing on my screen. What's the kVA of this transformer?
Oh, it's 100 kVA.
100 kVA, good deal. Mr. Embry,
Yes, sir.
I need to convert this kVA into watts. What's the wattage of this transformer?
Impedance is 4%.
Nope. That's not my question.
Okay, I'm sorry.
What was your question again?
It's a 100 kVA. Mr. Lennon got that for us. What's the wattage output?
100,000.
That's for
100
Mr.
watts?
Embry.
Oh, I'm sorry.
What was that,
Or
Embry?
100,000 watts?
100,000 watts. 100. Make sure I got enough. 100,000. There you go. So 100 kVA equals 100,000 watts. Let's see, Jordan Clark. Well, Jordan was just there.
He was just there.
No, I don't see
There
him.
he is.
I'm here. Sorry.
Hey, man, what's the impedance on this transformer? Percent.
4%.
4%. Okay. 4% impedance. I'm gonna put IMP. All right. Professor V, if you want to call out names here because I'm screen sharing, I can't see the full class.
Okay, you go down.
I want to know. Pick somebody.
Spencer.
Spencer. Spencer.
Okay.
All right, buddy. I need to convert 4% into regular decimal. What is that number going to be?
You can repeat it.
I need to convert 4% to decimal. What do I need to do?
You need to move the decimal point over 2 places to the left, right?
Yeah, and what would that make that 4% be?
0.04.
0.04, thank you. All right. Now remember, impedance is always losses. So I need to take 100,000. That's 10,000 times 0.04. Pick on somebody there, Professor V.
Randall.
Yeah. What was the question again? I was listening. I was reading the 2010 year of manufacture on the thing.
Okay.
I can't read numbers either.
100,000 times 0.04 on a calculation.
Okay. Point. 4,000.
4,000. All right. 100,000. 100,000, 10,000, 1,000 minus 4,000 equals
96,000.
96,000. All right. This is where you guys need to watch closely here. What is my original question?
What is the wattage?
Nope. It's right there on the screen.
What is the true KVA for this transformer?
There you go. My answer, because I had to figure in watts, is still in watts. What's the true KVA?
96 kVA.
There you go. Excellent. I just need to move over 3 decimal places. Bam. 96 kVA. Now, the only difference here, the thing you need to look out for is the question itself. What is the true? If I had left this, if I had made this wattage, you would have just left your answer 96,000. If I would have put this KVA, you would have come up with the answer you've got, KVA. Simple as that. Are we feeling warm and comfortable about how to figure out impedance on a transformer percentage-wise?
Yeah.
Yeah.
All right, good deal. If you got any questions later on, we'll keep on going with this. So that finishes percent and percentage. I know we spent some time on it, but a couple other things are going on here. One is
Sorry, go ahead.
what to read off the nameplate and how to figure impedance into a transformer.
What will we, I guess what would be the application for us knowing the math for this?
If you get, all right, where would you use this in the real world? For real? Is your question?
Yeah.
Okay. If you get into situations, and we'll just carry on a little bit more with percentages. All right. Every single transformer that's made will go to 150% for a short term period. Now, guys, there's no real 15 minutes, 30 minutes, 1 hour. There's no real set time. but all transformers, depending on the temperature, typically when it's hot is going to be the worst, will go to a 150% value for a short-term period. And after that, they'll just be an overload and they'll take out fuses and they won't operate anymore. So let's go the simple value. Let's just use a 10 kVA because it's a nice simple number. What will that transformer do in overload?
So whatever 150% times 10,000 is.
There you go. I mean, I would probably, I'm not doing a conversion for wattage or anything like that. I probably just leave it the way it is. Move your decimal place over 2 spots, so that's 1.5 for the 150%, and multiply it by 10.
So 15,000?
Yeah, 15. All right. I left it 10, that's kVA, so I'm not converting it to watts, 15,000. I'm just gonna leave it kVA. You're going a little bit, you're going back to the impedance. Right now, all I'm doing is figuring 150% of kVA. I'm not doing anything with wattage anymore. So it'll do 15 kVA. All right. If you get into situations, and here's how the industry works, they want their transformers to perform at 100%. Now this is optimal. 100% of the time. You're getting your best value out of the transformer that you can get. If it goes into overload, say, and we'll just use a situation here, say it's a nice calm day and it's 75 degrees outside and my transformer is running right at 100%. That is great. Fantastic. I'm getting the most bang out of my buck out of that transformer. Well, what happens when it's summertime? What happens when it's summertime and it's 103 degrees outside? What's the transformer going to do? Ah, geez. Get off that screen. Is the transformer going to go to 120%? Maybe 130%? Anyone?
Will it overheat?
It'll go to 120 and 130%, but we can go to overload to 150 for a short-term period. That's okay. Obviously, we're not going to go out every summer and change transformers out, are we?
I hope not.
No, because there's hundreds of thousands of them in our system. So it's going to go up a little bit. As long as it doesn't break the 150% point, we're good to go. All right. Goes back to a nice calm day. It's 100%. I think, you guys got to realize here, my transformer, this 100 kVA transformer is going to cost me about $10,000 a piece.
Damn.
So, they're not cheap. So I want to get the most I can out of this transformer all the time. And that includes seasons. If I'm at spring and fall and it's nice calm days outside, I'm not using electricity, I want it to be around 100%. When it gets real cold or real hot, it can go over a little bit, but I don't want it to break 150%. It's a fine line we're trying to drive there. Does that make sense, Embry?
Yeah.
Okay. The thing you got to look out for is when you're talking these fine values right here. All right, I've got my 10 kVA converted to 15 kVA, so I can get 15 for it with it. I've got 5 kVA to play with. What else do I need to factor? I'm not really getting 15 kVA out of this transformer 150%. Why?
Because of the impedance?
Because of the impedance, right. Okay. Now, engineers are going to help you out with this, but impedance is really limiting the amount of kVA I can get out of this transformer. So I've got to factor this also. I want it running at 100% almost all the time. That's my goal. If it goes to 150% or 120 or 130, that's okay. If it gets to 150, that's not going to last very long. But if I did not factor the impedance on this transformer, it's not 100 kVA anymore. It's a 96. So that's where it factors into my calculations as far as being able to use it. It goes back to the ball field that you talked about. Remember the 15 kVA I had?
Yeah.
Yeah, if you put 16 lights out there, will it work? Sure. I can go to
For a short amount of
150%.
time.
I can go to 150% in it. But what have I not taken into consideration? Impedance.
The impedance.
The impedance. There you go. Does that make sense?
Yeah.
Excellent. Good question. Good question. Okay. Any other questions on impedance? I mean, excuse me, on a percentage in impedance. So do remember this. And when you're looking out there in the world, all transformers will go to 150% for a short time period. All right. Your engineers and your system want to try to get 100% out of them 100% of the time. It's cost effectiveness. If I've got a 25 kVA transformer and 10 1,000 watt lights, is that worthwhile?
What was that last part? You kind of cut out there.
If I've got a 25 kVA transformer and I've got 10 1,000 watt lights, is that being cost effective?
No.
No, man, I've got 15,000 watts to spare. It's just not, I'm not using that transformer for good use. And I've pretty much thrown away $1,500 worth of transformers just sitting there doing nothing.
Would that make a transformer last longer?
No. No. As far as a transformer, especially a utility transformer, as far as a transformer is concerned, you can look this up on the internet. It is one of the most efficient pieces of equipment out there in the world. What makes it the most efficient? No moving parts. There you go. No moving parts. Okay. I think we pounded percentage here pretty hard. And I think we're all good if we come up to a quiz on it. All right. So unit 18 in the book, interest. Well, what's the difference between interest and next part? I can tell you right here. What's the difference between units 18 and 19? What's the difference between interest and discount?
Interest, you pay more. Discount, you pay less.
You're right. Interest, you gain. Discount, you take off. So any number that I use out there as far as calculating interest and a percentage, if I'm adding to it, that's interest. If I'm taking money off of it, that's discount, or whatever the number is. So I'm going to zoom through those real quick. Okay, unit 20, averages and estimates. These are real simple. I'm just going to leave the share screen up. Go huge. All right, averages and estimates. Okay, I've got tickets for the day, and I've got services I need to install. One's 200 feet, excuse me, 200. One's 220. One's 120. One's 300. One's 345. How do we figure average?
Add them all up and divide by how many you have.
Correct. Add them all up and divide by the amount that you have. So I've got 1, 2, 3, 4, 5 services. Add all those numbers up.
You're 237.
Well, it's got to be higher than 200.
1,185.
1185. Okay, add it all together. Those numbers equal 1185. Like we said before, we've got 5 different services we need to install. So that's going to be divided by 5.
So 909.
No. 1185 divided by 5.
237.
237.
Oh, I see. It.
Okay.
Oh, okay. I thought it. Yeah, I was coming to the end result. I'm sorry.
Okay. Okay. Nigel, you got all the way down to here. Yeah.
Yes, sir.
Okay. I just wanted the
I'm
addition first.
Yes, sir. I'm sorry.
No problem. No problem whatsoever. To be honest with you, you're not going to be working with in the industry with averages much. But you're still going to know how to do it. All right. Let's see. Estimates. All right. I don't really like to go into as far as the electrical world, and Professor V could probably jump in on this one too, of estimating something because I don't want to come up short. And we've already seen the situation where we need some wire. Do we always add a little bit to it?
Yeah.
Yeah.
Yeah. We always add what percentage?
10%.
10%. And sometimes if I'm sitting there at 998 with my 10% included, I'll just go ahead and say 1,000. All right. Try to stay with, as far as, getting material, looking at conductor, try to stay away from estimates as possible and stay more closely to actuals and adding some more to it. Now, there is something I'll teach right here, and it's a good thing to know out there in the world. The typical person in, let's see, Army or Marines, you might know this. You probably know this from being in the Marines. What's the typical gait or walk step in distance of a person? So I'm walking down the side of the road and I take a step from one foot to the other. What's the typical distance that I traveled in feet?
Probably like 3 feet.
Yeah, that's a good estimate for each individual person. And when you're out there doing work, don't accentuate your step. Just walk like you would normally walk. Equals 3 feet. So if I'm walking, let's say I need to get some wire from one pole to another out there in my field. If I walk and I've walked 30 steps, well, how many feet is that? Be careful.
90.
90 feet in steps. How much wire am I going to get?
Like 100.
There you go. Yeah, really it's 99, right? 30 steps, 90 feet. 10% of that will make it 99. Just go ahead and say 100 and be done with it. That's why I don't like to, what you do not want to do in estimates as far as that is concerned, is stand at one pole, look at the other pole, that looks like 30 feet. That's an estimate. Always step it off. Always add 10%. Professor V is probably pretty good at it. I'm decent at it. I can look from one point to the other and say, 100 feet. And we're pretty close. That's because we've done it so long. But as far as you guys are concerned, don't estimate. The guys on a job site is going to ask you, hey man, how much wire we need to get down this street? And if you look down the street and say, looks like about 1,000 feet. That's an estimate. What do you really need to do?
Pace it off.
Pace it off. Then add 10%. If you're right close to a number, say you're at 1150, shoot, make it 1,200. All right. No company is going to get upset for that little bit of stuff that's left over. And typically, those pieces that are left over, as far as your footage are concerned, are used anyway while you're doing your work. Professor V, anything you want to add there?
No, I'm good with that.
Roger that. Thank you. All right. Section 5, page 106, powers. We're getting into powers and roots. This is pretty simple. V, do you have the quiz up for today?
I'm looking at it now.
Okay, let me know if I'm missing anything there. Should be right on the book.
Yeah.
All right. The basic principles of powers. I'm on page 106. The power of a number is also known as its exponent. If a number is squared, for example, it is raised to the second power or has an exponent of 2. The exponent is a smaller number written above and to the right of the number as shown. This means that the number is to be multiplied by itself. So if you've got a number value and the exponent number up there, you multiply that number by itself that amount of times. So what they have there is 5 squared, which always is 5 times 5. That equals
25.
25. Okay, plain and simple. What if I have 5 to the 3 exponent? What's my math? 5 times 5 times 5 equals 25 times 5.
150.
25 times 5.
125. Or 125. Sorry.
125. Okay, and that's the simple part of whatever the exponent is. That's the number, small number to the upper right. You take that number and you multiply itself by that amount of times. Any questions there? Okay, moving along. Roots, square roots, is the opposite direction of what we're looking at as far as powers. So we'll go in the book, the root of a number is the opposite or inverse of its power. The square root of a number is determined by finding which number is used as a factor twice will equal the given number. The square root of 36 is 6 because 6 squared equals 36. So the numbers in a square root must be the same. All right, they're math that they have right there. The square root of 36 equals what?
6.
6 times 6. The square root of 27 equals what?
3 times 3 times 3.
3 times 3, which is 9, times 3 equals 27. And you'll notice in square roots, the numbers must remain the same. I can't have 3 times 8 to get a square root. These must all be the same to be able to determine square root. Now, plain and simple in a calculator, when you're using a calculator. Any questions on square roots? What you see on the quiz will be very simple. Now they got combined operations. All right, here we go. I am on page 122. And we're going to start talking about metric measure. Now, as far as the industry is concerned, do we use metric measure or do we use, as far as footages and whatnot, do we use that or do we use regular imperial US foot, yard, mile? Standard, okay. On math though, when we start, you just saw it in KVA. When we start working with math though, we're going to use the metric values. I will let you know. And if you look, has everybody got their chart in page 122?
Yeah.
Okay. Pico, nano, micro, milli are not existed in the industry. You won't see those used at all. Base unit, obviously. So that's ones. Kilo, we just saw. That's 1,000. Mega is used. And giga is used. So those are the ones that pertain to the industry. Base unit is 1. Kilo, 1,000. Mega, 1 million. And giga, 1 billion. Those are the ones that are used in the industry. So if I have 1 megawatt, how many watts is that?
1 million.
1 million watts, okay? If I have 50 kilovolts, how many volts is that?
50,000.
50,000, because I said kilovolts. If I have 1 gigawatt, what is that?
Billion.
1 billion watts, okay? Those are the ones that pertain to the industry there. Base, kilo, mega, giga. All right. And measure. Oh, gee. I'm on page. Is it break time yet? No.
Yes, 9:18.
These are pretty simple ones, but you guys do need to know them. I'm on page 131 right here. How many inches in a foot?
12.
How many feet in a yard?
3.
All right, skip the yards per mile. This one is very important. How many feet are in 1 mile?
5,280.
We keep that thing locked in your head because the industry, the manufacturers and industry have kind of worked this out, and they try to, in most cases, fit 1 mile of conductor on wire reels. So make sure that you know how many feet are in a mile. If I need to go a half mile or whatever, know how many feet are in a mile. The millimeters, like I said, we don't use, and there's no need for us to convert English to metric because we don't use those in the industry at all. Feet, inches, feet, and mile. How many feet in a mile? We are jamming through this book. All right, area measure, page 140. Professor V, do you have that question up that we have on the test? The quiz? I know we got one of these things.
What's the question again?
And we're doing the area measure question. You can find that for me. All right, English area measure. How many square inches are there in 1 square foot? Well, how do you do the math? How many inches in a foot?
12.
12. You take one side and you multiply it by the other side, equals what?
144.
144. There you go.
Okay.
So 12 times 12, 144. Have you found it?
Yes.
All right, what's the question?
How many square inches are there in 1 foot?
How many square inches are there in 1 square foot? There you go. You already got the quiz question. All right. So whenever you have a square foot question or square inch question, you multiply one side of it by another side of it. So I've got something that's 24 square inches. What is that in square feet? 24 times what?
288.
Why do you say 288? Why is it not? Because this is the common error that happens out here. Why don't I just go 24 times 24?
Yeah, I did the math wrong.
Are you sure?
Yes, sir. It's 576.
Are you sure?
24 times 24, yes.
All right. You sure it's not 24 times 12? This is where the question comes.
Yeah.
There
24 times. Yeah, okay.
There you go. People make that common mistake because I did the 12 times 12. That is in inches, and that is a foot. I'm asking for square inches and square feet again.
Yeah.
24 times 12 equals what? I think you had it right the first time. 288.
Oh, yeah. So I was right the first time.
You were. 288. Oops.
That's what I was saying, because it would just be double of the.
Right. This, if I'm asking for square feet, that remains the same. I changed my square inches. So you were correct. All right. My goodness. I want to get into. Professor V, can you look there? Do we have anything on mass or volume, square feet?
No.
Okay, we took that off, right? I want to get over here to ratios quickly today.
Yeah.
And we've already done energy in kilos. Measure. All right, yeah, so that is the next section. All right, guys, so let's take a break here because we are gonna get into the deep stuff. Ratio and measure. It is 9:22. Let's say 9:35. 9:35, let's come back. Bingo. This meeting is being recorded. Okay. So let's talk about transformers here a little bit. You should have a share screen going on.
It is.
Okay. This is normally the only number that you're going to see on the transformer that it gives you an indication to its size. Some companies do put further information down below it, but this is one that's vitally important. What's the KVA of this transformer?
25,000.
It's 25.
Yeah. You got to watch out for that. I've heard people say that, a couple of people. You got to watch out for the question. What's the KVA of this transformer?
25.
25. How many watts will this transformer produce, Embry?
25,000.
There you go. There you go. Okay. Watch the question. All right. And remember, that's in Lyman's terms. So let's talk about it a little bit. All right. Of course, the tank itself. Right. Typically filled with oil right up to this line right here that you see here at the top. So it's oil immersed, the core's all inside. You got lifting hooks on the side of it right here. Can anybody determine by looking at this transformer, and I'll just go ahead and repeat what Ryan said earlier this morning. What's the transformer's purpose? Converts high voltage to low voltage. Well, where's the high voltage side and where's the low voltage side? I'll give you a hint. Insulator size is a great indicator. The higher the voltage, the bigger the insulator.
They look about the same size, though.
Huh?
They look about the same size, though.
Where's the high voltage side and where's the low voltage side?
Okay.
There you go.
So top is high voltage and on the side is...
Right. Top is high voltage, bottom is low voltage. Now this is going to go on through all of your careers. The bigger the insulator, the higher the voltage, the smaller the insulator, the lower the voltage. So I have a high voltage input on the top and a low voltage output on the bottom. I'm going to get to another share screen here in just a minute on the Wacom, and well, I'll just go ahead and ask the question. I'll close my door here real quick. Why do we transform voltages? Why is there transformation in utility systems?
Because you can't have say it's like 25,000 volts going into a house. It'll blow everything in the house.
That's one great reason. What's another?
Safety.
Well, safety is going to factor in to that answer that we had, obviously.
Efficiency.
Efficiency. Well, okay, you bring up a good term there. What makes it efficient?
No moving parts.
Well,
no. Why transformation itself? Why do I use transformation, and why does it make my system efficient?
Well, I mean, it's similar to that point you bring up earlier with the you said with the 25 lights and what I forgot the amount of kilovolt amps transformer that you said earlier, but you want to make good use. It doesn't make any sense bringing X amount of a certain amount of kilovolt amps if you're not going to use it entirely in a particular area.
All right, that's part of the situation. We want to be efficient in our transformer. Clear all drawings. Do you see a share screen of a whiteboard?
Yep.
Yeah.
Fantastic. Fantastic. All right, guys, let's get all of this stuff out of the way. Perfect. Let's see if I'm going to draw now. Yay, I'm able to draw. Okay. Remember my water line analogy that I had going on there?
Yeah.
Okay. And we're gonna talk flow here for just a second. And flow translates into amps. Okay. The bigger my pipe, you see my pipe right here. The bigger my pipe, the more amps can flow out of it, correct?
Yep.
All right, so the more flow I can get out of my pipe. Now I'm going to put 240 volts as my pressure right here. So I've got 240 volts of pressure and my flow is coming out pretty well because I have a big pipe. I'm going to make a small pipe. Okay. And I'm going to use the same amount of voltage right here, 240 volts. Do I get the same amount of flow out of this pipe as I do the top pipe?
No.
No, because I made the diameter of my pipe smaller. Think of this in relation to conductor too. Okay, conductor's big, conductor's small. But now that I've lessened the size of my conductor here, I can only get so much flow out. Now, guess what happens? I'm going to use the same pipe that I just previously used. Think of this in size, but I'm going to raise my voltage by double. All right, and I'll take my flow out. Once I raise my voltage, this is an electrical property, my amperage will decrease. Okay, voltage raise means amperage decrease. Really, I've raised my pressure.
Because you're restricting the flow.
That's resistance. We're not in resistance yet.
Oh, okay.
Okay. I've increased my pressure here. So now I'm able to push my amperage harder out of the pipe. So what I was able to do at 240 with a big pipe, I'm now able to do at 480 with a smaller pipe. Make sense?
Oh yeah, bro.
Yeah.
Just raising the voltage.
Because I raised my voltage, I made my pressure push this out harder.
Okay.
Pipe. Okay. So really, if I've got 240 here, I can cut my pipe in half here at the bottom because I've doubled my voltage. Amperage remains the same, and we'll just throw a number here, 10A. Okay. This is not going to work. I'm only going to get 5A out of this because my voltage remained the same. But seeing how I raised my voltage on the bottom one, now I'm able to get 10A again because I've got more pressure on it. Here's the cardinal thing to watch right here. Raising voltage will make a drop in amperage.
So now, how, on the 480 pipe, if we increase the voltage to 480, wouldn't the amps go down to like 2.5?
Where do you get 2.5 from?
I was just going off of like your 10 amp, 5 amp.
No, don't worry about that one. 240. All right, and I'll put some sizes to it. 2-inch pipe. I'm able to get 10 amps out of it. All right, 480, 1-inch pipe. I'm still able to get 10 amps out of it because I raised my voltage. Voltage raise, amperage drop.
So yeah, but the amps didn't drop though on that one.
Yeah, they did. I'm able to, in this size conductor. See what I'm saying? I'm able to get more, the same amperage, I'm sorry, the same amperage through this pipe as I am through the 2-inch pipe because I have lowered my voltage. Let me go another route.
I'm looking at it backwards.
So
I'm looking at it backwards.
Because he has less resistance on the 2-inch pipe.
Yeah.
Well, it's resistant, the pressure.
Gotcha.
Pressure. Okay. So you remember your transformer picture? I'm going to draw one in a fashion like this. So here's my top bushings on the top, the square transformer. Here's my bushings on the bottom, and I'll tell you what these bushings do. Okay, for electricity to flow, you must have a complete path. So one of these go to ground. I'm going to inject in this one 7,200 volts. And I will let you guys know, every time that Professor B teach about voltages and we do stuff like this, we use actual system voltages. So 7,200 is a typical distribution voltage. This center one is neutral and goes to ground. So that's my neutral wire. I'm going to get 120 out of one leg and 120 out of another leg. So both combined equal what?
240.
240. Now I'm going to do this real quick here. Well, I'm not going to do it quick. I'll do it the way it should be done. How's that sound? What you guys are going to have to do is, as far as doing these computations, is figure out the ratio of the secondary to primary voltage. And it's really easy. And this is, as far as this book is concerned, we're hardly ever going to touch these chapters, but we're going to do a lot on ratios and proportions. All right, so what are my two voltage numbers? 7,200. It's transformed 240. So let's take 7,200 volts and divide it by 240. What is the answer?
30.
30. So for every one of these, I have 30 of these. 30 times 240 equals 7,200. Everybody get that? Any questions there? All right. New transformer. 7,200. 240. 1, 2, 3. Wire. Goes to ground. We've already determined 1 to 30. Excuse me. I didn't mean to do that. Where's my eraser at? And go back to the draw. What? There. 1 to 30. All right. Keep track of that number. So far, we've talked voltages, right? 7,200 in, 240 out. Now I'm going to turn something on in my house, and it's going to draw at my house 30 amps. How many amps are flowing through the primary side?
7,200
amps.
Oh, amps.
7.2. Or
this is part of your calculation now. I've got a 1 to 30 ratio. We're working on ratios.
So is it for every 1 volt, it's 30 amps?
You guys, here, look. Don't combine the two. We have figured by the transformation voltages, we've got 7,200 and 240. That's what the transformer does. That's what it's made for. That's how it comes from the factory. That is a 1 to 30 ratio. Now, when I start applying other numbers to it, amperage, most importantly, this is my key. So what I'm going to do here, I'm telling you, I've got a 1 to 30 ratio, and there are 30 amps on this side. I'm looking for how many amps are on the primary side. I'll give you a great one to go by. If I've got this number, I divide. 30 divided by 30 equals what?
1.
1. There's your answer. All right, watch this. I don't know if I can do. eraser. Let's see if I can do this part. Obviously, you've got to figure out what the ratio is by voltages, and we'll give you those numbers, just like I did here. I got to figure out the ratio. Then we're going to have to give you, as far as a test or quiz, or you're going to be out there in the field taking measurements with a meter to find out how many amps are on this thing. Okay, so let's go this direction. I take a measurement and I've got 2 amps on the primary side. This is the high side. How many amps are on the secondary side? If I divide it going up, what do I need to do going down?
Got to multiply it.
Multiply it. There you go. So how many amps do I have on the secondary side?
60.
60. Perfect. Y'all getting the gist of that?
Yeah.
Okay. Okay. Perfect. Perfect. All right. So, well, I mean, it comes to, you got Ohm's law? No, we won't get into that. That's Professor V. That was 4, right? Quiz 4?
That was quiz 3, I think.
For Ohm's law?
Ohm's law started quiz 3.
Okay. I don't want to get too far ahead of them. Let's do, let's see if we can do some calculations on our own. My primary voltage, I'm not going to draw the transformer anymore, is 19,900 volts. That's primary. My secondary volts is 480. First, figure the ratio. Now, if you come down to a decimal number, that's okay. So how do I figure the ratio on this transformer?
19.9 divided by 480.
There you go. Let me know what you got. There's a train coming somewhere.
41.458 repeating 3.
All right. So for every one of these, I have 40, what?
41.458.
We can round. That's close enough for us to the 100th. So every one of those, I have 41.45 of these. That's our key. I have 10 amps on the primary side. How many amps do I have on the secondary side?
41.
Nope. 10. What do I need to do?
Multiply.
Multiply.
Right, equals 414.5, right?
14.5, yeah.
Answer. Perfect. You just done one all the way through. I'm going to use these same voltages right here. 1 to 41.45. My secondary amps is 626.
You divide.
Right? Go.
$15.10.
15.10. You guys are getting good. Is everybody up to speed on how this works?
Yeah.
Okay, cool. Cool. 15.10. Now I'm going to give you an extremely difficult one. And remember, we'll talk about it when we get up here. Clear off. I'm going to be at my generating station, and the voltage is 115,000 volts. At my home, I'm using 240 volts and 10 amps. How many amps are on the transmission line?
$479.
No,
Oh, wait.
115,000 divided by 240.
$11,500.
Everybody the same?
Yep.
So
I
for
got
every,
one. So for 115,000 divided by 240, I got 479.16.
you got what?
479.16.
Okay.
That's what I got
Yeah,
too.
that's what I got.
Okay. So for every one of these, you had, and say that I had
479.16.
4.16. Okay. And I've got 10 amps on this side. Now this is where it gets kind of squirrely. You need to watch your math. All right. What's 10 divided by 479.16? Not 479.16 divided by 10.
Yeah, that's what it is.
Got to go direction here. I'm actually have to go backwards. What's 10 divided by 479.16? It's going to be a decimal, that's for sure.
0.020.
Say that again.
0.020.
All right. 0.020 is on my transmission line voltage right here. Now, what did we talk about earlier? How high is my pressure here? Really high. How high is my pressure here? Really low, right? So I've got to have a pretty decent sized pipe to get that 10 amps through that pipe. What kind of size pipe do I need over here?
Small.
Yeah, right? Real small. So this is really in the concept of transformation, the full process of transformation and doing ratios and raising voltage and lowering voltages in the process is why we have transformation. A transmission line, I don't know, well, I'll just draw it on my screen right here. A transmission line from a power plant or a generating station going to a substation is typically, Robbie, if you could probably help out here.
Yeah.
No bigger than that, and that actual size. Okay. How am I able to squeeze all those amps in there? I raise my voltage, my amperage does what?
Lowers.
Lowers, okay. That, and then I'm going to go down, I'm going to transform it so I can take it down to a lower voltage, and then a lower voltage till finally it gets to my house. And I have seen some businesses with conductors this same size. Well, obviously, I can't do that all the way from the transmission station. It's conductor. It boils down to conductor size. I cannot, from a generating station, have a conductor this big around to be able to carry the amps that I need to carry. It's just, I can't fit it on a reel. I can't install it on a pole. It's way too heavy. Right? So I can, and actually right now as we sit, the transmission feed for us right here at the college is coming from Georgetown, Winyaw. So that there's just no way that I can get that size conductor all the way from Winyaw to here at the same voltage we're using here. I have to raise that voltage so my conductor size can get smaller to be able to get transmission, then distribution, and then finally into this building. Make sense?
So before transformers were made, were the lines like considerably larger?
Well, transformation has been around almost since the transport of electricity has begun here. They've been around just as long. When who was it? Edison was DC. What he had was more of generation. He had generation in little buildings or basements, and the generator would feed your house in DC. Well, of course, that went away real quick. What took over? Who took over?
AC.
Yeah, and who's the man?
Tesla.
Nikolai, yeah.
Yeah, Tesla.
Nikolai Tesla. Okay. He started going with AC. Now, as far as transport distance, I've got a conductor here, and I'm going to go 100 miles to the end. As far as transport distance, DC is more efficient. As far as being able to transform it and not have to get huge conductor sizes, AC is more efficient. We'll talk more about that later. Okay. So General Electric, Tesla, and who's the guy? I can't remember his name that started the first plant up there at Niagara Falls. General Electric were the first ones to transport electricity. Now, on a whole, you're looking at a transmission substation. What are you talking, Robbie? 50 to 75 miles maximum?
Yeah.
So you got generating stations that are, placed about to be able to transport to that. Even at that, I mean, 75 to 100 miles is not a pretty sight. You're gonna have to have plenty of generating stations, and then transformation to be able to get it to a home. Does that answer your question?
Yeah.
Okay. All right. So, I mean, big thing to remember: once I raise my voltage, my amperage is going to drop. Now, on the other side, if I start using a lot of amperage, say I'm using 1,000 amps here in my pipe here at the bottom, is my voltage going to drop? Does it work both ways? If I raise my voltage, does my amperage drop? Yes, we know that. If I raise my amperage, if I start drawing too much, what happens to my voltage?
Goes down.
It's going to go down too. Okay. But your system, your generation is going to say, I need to give it all the pressure that I can until eventually you're going to blow a fuse or melt a fuse out. So there's protection for that not to happen. All right. Well, good. I'm glad you guys caught on that, because this is going to come into factor a lot of times, especially when you start determining ratios and sizing transformers. You guys are going to actually be able to. I'm going to give you a home or a business and say, this is the voltage that I have, and I'm going to draw 600 amps. You guys will be able to size the transformer that I need there, and you can be able to tell me what kind of fuse that needs to go in that transformer. And remember, here's the things. I want it to be where? At 100%, and maybe if it has to, go to 150% for a short-term period. So all of these things add up. I also need to know, heck, will it be okay if I have a 5.6% impedance on it? So all these kind of boil down to one thing. Is it an engineer's job typically to do this on a new installation?
Yeah.
Yeah, it is. Especially with big name companies, Duke Energy, Santee Cooper, Ori Electric. You're going to get a piece of paper. It's going to tell you what to do. Now, I've had plenty of other ex-students that have graduated from this class that are working for smaller utilities that have called me at 10, 11, 12 o'clock at night. Professor Shoemaker, I've got a transformer here. It keeps melting out the fuse. What do you think I tell them?
Check the voltage.
Check the voltage. Number one. Check the amperage, as best you can in that short amount of time. And if your voltage and your amperage are over the size of the transformer that you need, change out the transformer. Well, of course, their next question is, well, to what size? So you're able to actually size the new transformer that you're going to be able to put in there. So just don't think, we teach it all. Just don't think you'll be able to walk out there in the world on a system and get all the questions answered for you. And I can guarantee you, Professor V, jump in on this one. You think you're going to get an engineer at 3 o'clock in the morning?
No. They're in the bed.
Yeah.
Monday through Friday, 8 to 4, maybe.
Yeah, your dispatchers will help you out. Your dispatchers are sitting behind a computer and they got calculators and all that kind of stuff. But you're still going to have to get those essential readings, get that information to them, and recheck yourself. Yeah. Here's what you don't want to do. And this is just kind of off the math and into a life story. I've got a 25 kVA transformer. Okay. It's not working right. Hey man, run a service server and get me a 75. Okay. So they run and get a 75, they hang it. The next day, an engineer comes up and says, well, really, you only needed a 37.5. So guess what you got to do?
Change it out.
change it out again, and then notify all those customers again. You're going to be without power because we need to change it out again. It's just a huge waste of time and money. And I can tell you one thing, the way days are today, you want to save as much money as possible. All right, Professor V, do I need to go any further for what's on the agenda today as far as quizzes?
No.
Okay. Do you want to do a quiz review? Well, what time is it? You want to do a quiz review and just cut it loose?
Yeah, that sounds good to me.
All right, sounds good to me. And I could be on the side here with my screen. So we're going to do a review on the quiz, and I'll write some stuff out as we go. Professor V, it's all yours.
Okay. 10 questions, guys. All right. I'm not going to give you the answers. I'm just going to.
Yeah, don't shout out the answer either.
Okay. Okay. What does for lineman KVA stand for?
KVA. What does it stand for? Okay. What's that? What's that?
Amp hours.
Kilovolt amp.
Told you not to say the answer.
Oh, sorry.
No answers, please.
No answers.
No answers. All right. Question 2. What does impedance mean?
So give us a short definition of what impedance means.
Okay. Not right in a second.
No, on the test.
Yeah. 3. Got to do a little figuring here. A 25 kVA has an impedance of 2.6%. What is the true kVA?
All right. Remember to watch out. I'm asking for the answer in kVA, not watts. So 25, and do your calculation on 2.6% impedance.
Right.
Okay. Okay.
We started on this last week, touched on it throughout the day today. Define volts. Okay.
And I'll tell you from here, I'll tell you out there in the field as far as working and everything like that. Does anybody know what KISS stands for?
Keep it simple, stupid.
Keep it simple, stupid. If you don't want to hurt somebody's people, keep it short and simple. Okay, that's what. All right. Keep it short and simple. If you give the definition that I've given, we all know what you're talking about. Okay, go ahead.
Okay. Number 5, define amps.
All right.
Okay. Question 6, define watts. And watts is power.
Yeah, we know that. We know the value for this. We know the value for that, the numerical, and we know this is power. But what's being done? How or what's being used?
Right.
Give that definition. Okay.
Number 7, what can a transformer be overloaded to for a short period of time?
Yeah. What's the percentage value?
Overload. Okay.
In overload.
Okay.
We're not asking for KVA. We're asking for that percentage number.
Right.
Okay.
Question 8, a 25 kVA transformer can be overloaded to what kVA? Okay. Number 9, a 50 kVA transformer is overloaded to 150%, has an impedance of 5.0. What is the true kVA?
Oh, wow. Okay.
Yep.
So you actually want me and put this transformer in the KVA it is in overload.
Yes.
Then do the impedance.
Correct.
Got you. Okay. So overload it first, then do the impedance on it.
Right.
Good one. Okay.
Okay. The last question we really haven't talked about, and we can show a video on it if you like. It talks about pulling poles. We want to continue with that one, or
What, that question that we got right there?
question 10, when pulling poles, you may stand between the pole and the truck when it is being pulled out of the ground, true or false?
Let's just use a little common sense there, guys.
Yep.
When you're pulling poles out of the ground, you got a truck and you're standing at the pole. Do you want to stand in between the truck and the pole?
No.
Headache.
Seems like a crushing hazard to me. Yeah.
Yep.
So I
That's
think
worse than a
we
headache.
got that one. Okay. Questions?
That was number 10.
All right. Questions, anybody? Okay. We went through a good bit today. And I will tell you this, ratio, proportion, and when we start getting to Ohm's law, we're going to dwell on that a good bit. I mean, that's really the meat and potatoes here as far as this math part is concerned. So we'll be on that a good bit. But you guys listened well. You answered well. Very productive day today.
Yeah.
Not even, what time are we? Oh, 10:15. Perfect.
10:15.
All right. So we will post on Remind when the quiz is available. I will post when the video is available. Listen here closely. The last quiz that we got right there. Obviously, some of you guys paid attention. Some of you guys watched the video. You took your time and got 100s. Some of you jumped on it real quick and you got 60s and 70s. Get those 100s, guys. Get those 100s. They're there for you.
Yeah.
Professor V, anything else you'd like to add?
We'll be here till what time? 4-ish?
4-ish, yeah.
Yeah.
Of course,
So,
you can always get us on Remind too.
Yep, just set us up, man. Don't just shoot on back to the room and ask questions.
Yeah, I think Nigel can attest to that one.
Yeah.
Yep. We're
Yep.
here for you.
Yep.
All right, gentlemen, have a good day. We're going to text you and let you know when it's happening.
Sounds good.
All right.
Thank you, sir.